Telepresence is common in the increasingly global workplace. While there are many advantages to this, there are also numerous disadvantages. Current telepresence solutions allow limited random casual encounters. Additionally, there is limited peripheral awareness. Users tend to have a very narrow view and cannot engage with or interpret their surroundings. We hope to add a physical element to telepresence using a humanoid robot and controlling it through motion capture. A user sees through the eyes of the robot and is able to walk around freely in their environment using natural and intuitive motions. Our solution uses a Now robot, a 60 centimeter tall humanoid with over 20 degrees of freedom. The user controls the robot remotely using a Vicon motion capture system. Infrared cameras watch trackers on a hat and shoulder pad the user wears. That information is used to assess where the user is standing and looking. The interface is entirely gesture-based. The robot walks forward when the user walks forward. The robot looks up when the user looks up. Here we see a user interacting with the system. We can see that he is shown a full view of what the robot sees, and simply by looking around himself, he can move the head of the robot and examine his surroundings. Typically, the user is shown a fully immersive view from the Now's camera. Laid on top of this is a virtual representation of the robot's body. This gives the user basic situational awareness of the robot's current body position. The view is always shown from the perspective of the back of the robot's head. This ensures that the view of the camera always has the same reference frame as the view of the robot. A circle indicates the direction of the user's gaze and helps him or her understand the behavior of the system. Blue indicators show when the robot's head is moving. The overlaying of the body on the camera feed is meant to provide fused information to the user. When they are looking at the feed from the camera, the robot's body position remains in their peripheral vision. When the user steps forward towards the screen, the robot walks forward. When the user steps back to their original position, the robot stops. The user can also rotate the robot's body by rotating their own body. With these two gestures, they are able to move the robot around in a room. Note that the robot always moves forward from the user's perspective. When the robot has his head turned 90 degrees to one side and the user moves towards the screen, the robot will actually sidestep in the direction it's looking. This moves the camera forward, so the experience from the user's point of view is consistent with what they are expecting. The interface automatically disengages when the user steps back or looks too far off screen. This stops unintended and unsupervised robot motion. When the system detects that the user is not looking at the screen or is too far back, it displays an abstract view of the room the user is standing in, with an icon showing the location and orientation of the user. This is especially useful as a user approaches the interface for the first time. They are given immediate feedback on how to engage with the interface and how the system detects them. When the robot falls, the representation of the robot's body will be updated to reflect this. In this example, the robot has fallen on its back, and the floor, represented by a black grid, can be seen up against the robot's back, which is an accurate representation of the situation. The video feed shows the ceiling, adding to the user's situational awareness. A message along the bottom indicates that the user should crouch down and then stand up again to recover the robot. This motion was chosen so that the action of the user standing up stands the robot up, re-establishing synchronization between the users and the robot's bodies. The intention of this system is to provide the user with a physical embodiment somewhere they are not co-located. It provides a gesture-based interface that is simple, uses body motion similar to moving around in the real world, and maximizes situational awareness. While this project is a step towards natural gesture-based interfaces for controlling the movements of a robot, it suffers from some technical problems, mainly latency between the user's movement and the robot's movement, and video quality. Improvements to latency and fidelity would significantly increase the usability of this interface, but as a proof of concept, we believe this paradigm shows significant potential.